Welcome, everybody. We've got today, Kelli Humbird is a design physicist at Lawrence Livermore National Laboratory. Most of her research is concentrated in inertial confinement fusion, and applications of machine learning to strengthen predictive modeling and optimize designs. In addition to ICF, she has spent time at LLNL working in stockpile certification and technical nuclear forensics. She is the PI of a project to accelerate atomic physics calculations with neural networks, and briefly worked on machine learning analysis for the spread of COVID-19 during the first year of the pandemic. The common thread throughout much of this work is the application of machine learning to scientific problems with sparse data. And with that, I will turn it over to Kelli.
All right, thank you. And thank you for being patient through those technical challenges. The fun thing about working for a government-sponsored lab is we don't have microphones or cameras on our laptops, and we can't install any software. So that presented some challenges for using Zoom. So yeah, thanks for being patient. And thank you for the invitation to come talk today. So I'm a designer at Lawrence Livermore National Lab, working in the inertial confinement fusion program, or the ICF program. So today's talk, I'm going to give a brief history of the program and the progress we've made over the last decade or so of research, kind of culminating in the big experiment back in December, which I think is why I was invited to speak here today, because you want to hear about that experiment. And then in the second part of the talk, I'm going to take kind of a personal spin on the story and talk to you about what my team does. So I currently lead a group of researchers that has been working on using statistics and machine learning to sort of improve our predictive capability of these really complex experiments. And for this particular experiment, all of our tools kind of came together to make this nice prediction of what would happen in this experiment with very credible data-driven uncertainties. So we were really proud of the result. And then we ended up being right. We predicted the ignition was likely to happen on this shot, and it did. So we're really excited about ignition, but also really excited about how far we've come in our predictive capabilities. So I'll talk a little bit about that in the second part of the talk. So next slide. Yeah, so this work is built on really decades of research by a huge team of people, both within Lawrence Livermore National Lab and the broader community, national partners and international partners. So it's a huge team of work that I'm speaking about today. By no means my work, huge collaboration. Next slide. So I want to give a couple specific thanks to a few colleagues. Luke Peterson is one of my colleagues. He and I gave this similar version of this talk a few weeks ago to a different audience, and also acknowledge the Hybrid E team, which were the team of experimentalists and designers that were responsible for this experiment. Next slide. Okay, so here today is because you probably heard something about nuclear fusion back in December in the news headlines. There were all of these headlines about achieving ignition and long-awaited fusion energy breakthrough. Maybe you've heard about that, maybe you haven't. If you've not, I encourage you to go watch like the 60 Minutes episode or something. You get a really cool glimpse into the facility and what the targets that we're fielding look like. So it's really informative and a cool glimpse into what it's like to work here at Livermore. Next slide. Even more exciting is that you know you've made it in your career when you're parodied on Saturday Night Live, or you have an Onion article written about your work. So clearly this result was a really big deal, worth talking about. Next slide. So why was there so much hype? Why were there so many news headlines? Why was there this big DOE press conference? And why do people care? Other than the fact that it's nice to see scientists succeeding. Next. So people are so excited about this result because the potential payout of releasing energy through carbon-free fusion reactions could be enormous. A fun statistic is the energy equivalent of the world's oil reserve is contained in about a cubic kilometer of ocean water. If you could isolate all the deuterium in the ocean water and use it for fusion fuel. So it's a very efficient energy source if you can figure out how to make it burn. And it's essentially, carbon-free, no long-lived radioisotopes and other things we worry about with current energy sources. Next. So beyond just clean energy applications, fusion has a lot of different applications that are valuable to us. It lets us study fundamental sciences and at extreme conditions, conditions similar to what you find at the center of a star or in planetary atmospheres, and conditions that are really difficult to create in a laboratory setting. Here at Lawrence Livermore National Lab, our main charter is to be stewards of the nuclear stockpile. So conducting these experiments lets us validate our models and make sure that our stockpile remains safe and secure. So there are a lot of different approaches to fusion that have been taken throughout its research history. Gravitational fusion or gravitational confinement is what happens in a star. You need a lot of mass in order to use gravitational confinement, not something we can do here on Earth. Two approaches that are common in the laboratory setting are magnetic confinement and inertial confinement. So we're going to focus on inertial. That's the type of research we focus on here at Lawrence Livermore National Lab. And there are different approaches to inertial confinement, indirect drive, direct drive, and magnetic based inertial fusion. So we'll be focusing on the first, indirect drive, which is what we do at the National Mission Facility, our premier experimental facility for ICF. Next. Okay, so the outline of this talk is kind of shown here. I broke it into two parts and then a third part that is a glimpse at the future of where we're taking this work. So in the first part of the talk, we'll focus on ICF physics and the kind of history of the program here at Livermore that's led up to this result that we had in December. And then I'll switch to kind of the part near and dear to my heart, which is the predictive modeling aspect of this work and how we used data-driven techniques to call the shot before it happened, and then a little bit about the future and where we hope this will go. Next. Okay, part one, nuclear fusion and the National Mission Facility, or the NIF. Next. Okay, so you've probably seen a curve like this before. This is the average binding energy per nucleon versus atomic number. This chart shows us why we're so interested in fusion if you stare at it long enough. So what we're seeing on the left side of this curve is if you take two light elements, fuse them together, they release a lot of their the excess binding energy and they create heavier atoms. As you work your way up this left side of the curve, the gradient is really steep. That means you're releasing a lot of energy for each of these reactions if you're climbing up this curve. You might be more familiar with the right side of the curve. This is how we get fission energy and current fission power plants. And that approach, you take a heavy nucleus, you split it apart and release energy that way. Always working your way up toward this most stable isotope, an isotope. So at Livermore, with our ICF experiments, the reaction we are most interested in is the fusion of deuterium and tritium. Deuterium is hydrogen with one neutron, tritium is hydrogen with two. When those two isotopes fuse, they produce a high energy neutron and a helium nucleus that we call an alpha particle. This is a reaction that produces a lot of energy, about 17.6 MeV per each reaction. So you can compare the energy density of fuel source to coal. It's a lot more than burning coal. Next slide. So the challenge with fusion is that in order to create the conditions in which the deuterium and tritium want to fuse, you have to get to really extreme conditions. So there's this kind of generalized criteria you need to meet with your plasma conditions in order to generate a lot of fusion energy. It's called the Lawson criteria. It's a product of N and tau. N is a plasma density and tau is a confinement time. So it's basically saying you have to achieve a high enough density for a long enough amount of time to exceed some threshold value in order to achieve ignition or produce it, kind of creating this self-sustaining burn wave where you produce a lot of fusion energy. So the two main approaches to confinement-based fusion are magnetic and inertial. They take very different approaches to meeting this Lawson criteria. So in magnetic confinement, they're focused on containing a low density plasma for a very long amount of time, several seconds, and they operate at atmospheric pressure in these experiments. Inertial confinement fusion does the opposite. It's focused on creating extremely dense plasmas that are, at 100 billion atmospheres, and we want to confine them for a very short amount of time, long enough to produce energy, but we're not going to confine the system for too long. Next. So the principal concept behind inertial confinement fusion is that of an implosion, or the act of squeezing a fuel pellet to extremely high temperatures and densities. This work really kicked off with a seminal paper in 1972 by John Nuckolls, who was a former laboratory director. He wrote this nice paper where they first proposed lasers as a way to compress a fuel capsule to create fusion energy. The focus on that paper and much of the early work was on the direct drive approach. So in direct drive, you have this fuel capsule filled with deuterium and tritium and an outer shell that we call an ablator. The lasers are directly, they're shined directly on this capsule, and they heat up the outer surface of the capsule, cause it to ablate. That accelerates the inner surface of the shell radially inward, compressing the fuel to extremely high densities, temperatures, pressures. This is actually the main approach to fusion energy that is being pursued at University of Rochester, the Laboratory for Laser Energetics. There are some advantages to laser direct drive, so you can get your laser energy coupled to your capsule more efficiently. But there's some cons to this approach too, in that you have a finite number of laser beams, and when you use them to compress this fuel capsule, you might have asymmetries in how you're compressing this capsule. So a kind of a grand challenge of ICF experiments is to take a spherical capsule and compress it spherically. You can think of it as trying to take a balloon and with your hands trying to squish the balloon to a smaller volume. If you don't apply pressure perfectly uniformly across the entire surface area of the balloon, air can start squirting out the sides, right, between. The same thing happens with our fuel capsules, and whenever you're compressing asymmetrically, you're not coupling as much energy into your fuel capsule as you'd like to. It's not as efficient of a compression, and so you don't performance. So a challenge with laser direct drive is you have a finite number of laser beams. It's hard to keep things symmetric in that case. Next slide. So at Livermore, we focus on an approach called indirect drive, ICF. So we add a horum or a radiation cavity to drive the capsule more symmetrically with X-rays. So rather than shining the laser beams directly on the capsule, we shine them into this gold cylinder called a horum. There's a cross-section of the horum shown on this slide. Just a little gold can. At the top and bottom, there are holes called laser entrance holes, the 192 laser beams of the NIF into the laser entrance holes. They heat up the gold wall of this forum. And as the gold begins to heat up, it emits X-rays. Those X-rays, kind of bounce around in this little gold oven and end up creating a pretty nice uniform radiation bath that will then heat up the capsule. So there's a cross-section of the capsule shown next to the forum. This is kind of a modern ICF capsule. We use high density carbon or diamond ablators for the outer surface of our shell. Inside this diamond ablator, there's a thin layer of deuterium and tritium ice. These are cryogenic experiments. And then there is DT vapor at the center of the shell. Next slide. So the implosion phase of an indirect drive experiment is very similar to a direct experiment. We have X-rays now, beams themselves, that will heat up the surface of our capsule, which is the ablator. As the ablator heats up, it begins to ablate or blow off from the shell. And when it blows off, it creates a radially inward force, equal and opposite force on the inner surface of the shell that accelerates that inner surface of the shell radially inward. At some point, it'll accelerate, it'll accelerate as far as it can and compress things as much as it can. And it will reach a point of minimum volume where the shell stagnates or stops moving. Stagnation is when the fuel inside the capsule really starts to burn. So we've gotten this central hotspot here to extremely high densities, extremely high temperatures, created conditions where the deuterium and tritium will be fused, producing this high energy neutron alpha particle. The alpha particle will stop in this outer layer of cooled fuel and deposit its energy and heat up that fuel to create more fusion reactions. And we call it kind of like a burn wave, will then propagate radially outward, consuming this cooled deuterium and tritium fuel and producing lots of energy. As this happens, the entire assembly begins to expand and eventually explodes. It disassembles and then the burn quenches. Next slide. So this is a slide that's not going to work, unfortunately, because this is PDF, but here we would have a video of what exactly it looks like to simulate one of these things using a multi-physics code. So we use this code called Hydra that models the radiation hydrodynamics associated with these experiments, as well as a number of other physics packages like atomic physics, your nuclear burn, any effects from magnetic fields, etc. So what you would see if this would play is you would see lasers enter the horum from the top and bottom. The horum walls will begin to heat up and expand as they heat up. Similarly, your outer capsule ablator will begin to expand as it ablates. It'll push this shell inner radially inward. This capsule will reduce in volume by about 30 times by the time the experiment is over. So it'll get really, really tiny. This experiment is designed using these codes. And if you look at the figure on the right, you see what a laser pulse looks like. So this is how we actually deliver the energy from the laser beams of the NIF to this horum. So we're looking at the power versus time here. And you'll see it's a very particular shape of laser pulse. It took a lot of work, a lot of learning over several years to figure out how to tailor these laser pulses to deliver the energy to the capsule in a way that results in good performance. So some things that we keep in mind when we're designing laser pulses are, one, accelerating the shell as fast as possible because the yield or the energy output of implosions increases greatly with the implosion velocity. So we want things to go fast, but we also have a lot of different types of hydrodynamic instabilities that plague these implosions that can, basically tear the shell apart in flight because you have small perturbations on the surface that grow as you compress it. And so we also have the challenge of making sure we keep this implosion as stable as possible. And we do that by basically controlling the adiabat, controlling how much entropy we add to the implosion as we're trying to compare with our laser. Next slide. So we carry out these ICF experiments at the National Ignition Facility here at Lawrence Livermore National Lab. This facility is pretty amazing. If you ever get the opportunity to come out here and visit and tour the facility, it's totally worth it. It's huge. It's about 3 football fields in size. A lot of that space is taken up by capacitors that store the energy that will be used to produce the 2 megajoules of UV light that we insert into our horums. So it's a big facility. The far end of this facility, there is a target chamber. That's where the experiment. It's a big target chamber, again, about 10 meters in diameter, but our targets are super tiny. So there's a picture of an actual horum here on the bottom corner of this slide that shows that our actual targets are about 1 centimeter in size. Inside this tiny horum, it's the size of a pencil eraser, there is the fuel capsule that's about 2 millimeters in diameter, so about the size of a pea or a peppercorn. So it's a really tiny target by a really large facility. These things are just absolute engineering marvels. They are created to perfection. The surface smoothness of these capsules is like one of the smoothest things that exists in the world that is man-made. So really, really impressive engineering that do these experiments that happen several times a month. Next slide. So NIF has a wide array of diagnostics that have helped provide the insight into our experiments over the past decade, build our understanding of what happens in these implosions. I won't go over the details of any of these diagnostics, but they're very well diagnosed, and we're always working on fielding new diagnostics and ways to improve the resolution of what we already have. Next. So in this next part of the talk, I want to go over kind of a brief history of what experiments at the NIF looks like over the last decade, starting with kind of our very first experiments that happened when the facility came online in 2011. So back when experimentation first started at the NIF, we were actually using plastic ablators. So our fuel capsules were made out of CH. We learned a lot about hydrodynamic abilities with these capsules. They were basically a lot worse than we thought they were going to be when we first started experiments on the facility. So a lot about pulse shaping was learned in those first few years of experiments in the NIF. And we went from producing, a couple kilojoules of yield up to about 15 to 20 kilojoules of yield pretty routinely by studying these CH capsules. Next slide. So while we were learning a lot with CH, we were also bringing up the capability to create diamond ablator capsules. Diamond is a more efficient ablator, and it actually lets us use shorter laser pulses at higher powers. This does a lot to actually help with the symmetry control of your implosion. We also reduced laser plasma instabilities by changing the horum gas fill throughout this time, and made quite a lot of progress over the course of about 3 or so years, going from 20 kilojoules up to about 50 kilojoules of neutron yield in 2019. Next slide. And then progress really started to accelerate kind of back in 2020. So we learned some new tricks and techniques to maintaining our implosion symmetry while also being able to increase the size of the capsule relative to the horum. When you increase the capsule, you're increasing the surface area. It is allowed to, or it's able to couple more energy from the horum to the capsule. So you're taking better advantage of the energy that you have. So learning how to do this is what enabled us to reach what is called a burning plasma state in late 2020. A burning plasma is where you are basically producing more energy through the generation of these alpha particles and their subsequent deposition of energy in cold fuel. Then you are losing at that time due to the expansion of your shell as it starts to disassemble. So it's a big physics milestone because it's kind of like right where things start to get interesting. And if you just improve your implosion a little bit more, you'll actually start running up the ignition cliff and producing a lot of yield really quickly with very small improvements. Next slide. So we actually saw that behavior experimentally. Right after we reached the burning plasma state with our experiments, we were able to make a very minor improvement to our Holram geometry. We actually just shrunk the size of those laser entrance holes by a very small amount. That reduced you're losing that hole throughout the implosion. And by just improving the Holram efficiency a very small amount, about 6%, we were able to field an experiment that produced 1.35 megajoules of neutron yield. So that was in August 2021. That experiment was also a really big deal. There were some headlines about it. It actually met the physics definition of ignition. It exceeded the Lawson criteria by quite a lot. But there was this other definition of ignition written by the National Academy of Science when NIF was first built that defined ignition as a target gain of greater than 1, which meant we needed to produce more energy through fusion than the laser energy that went into the system. So this experiment had 1.9 megajoules of laser energy for a target gain of 0.7. What was really nice about that experiment, though, is it let us do some interesting physics studies in this ignition regime. So we actually took this experiment and attempted to repeat it several times over the course of the next months. Repeating an experiment is difficult because you can't reuse the same target twice. Once you've shot it, it's been destroyed. So you try to make the same target again. But we actually learned that, really, really tiny differences from one capsule to the next can have a huge impact on your performance. So I'll talk about these repeat experiments again later in this talk, but they provided a really nice set of data for us. Next slide. And then things kind of accelerated again pretty quickly back in December. Again, we had a very minor upgrade that enabled us to improve our performance greatly. The laser facility was able to make some changes to the laser that let us go from 1.9 megajoules of our maximum energy to 2.05 megajoules, so just an extra 150 kilojoules. This allowed us to drive a slightly thicker capsule, so we added more mass to our ablator. This helped with some hydrodynamic instability. And just these two small changes let us get to the result we had in December, which was producing about 3.15 megajoules of neutron yield with the 2.05 laser energy and 0.5. Next slide. So to kind of summarize this section, fusion research kind of looks brighter than it ever has at this point in time. It took us longer to fusion ignition on the NIF than we originally envisioned when the facility was dreamed up in 1990. But now that we've the definition of ignition, we can kind of pursue those original goals that we had for the facility for scientific what materials look like at these extreme conditions. NIF isn't a fusion. It's not a very efficient facility, and it's built on 1990s technology. But through this demonstration, the ignition can be achieved in a laboratory setting. We've kind of laid to rest some of the fundamental physics questions about whether or not fusion energy is even worth pursuing. And maybe there are a number of startups that are currently attempting to leverage this advancement to make production. Progress was very incremental. There was no one big thing that happened that led to the December experiment. It was a lot of learning and a lot of trial and error and advancements in engineering and diagnostics and our simulation capability that improved over time that led to that result. We were actually scheduled to repeat that experiment in February. Fortunately, the target failed. There was a leak in the capsule, so we weren't able to actually do that experiment, and we're scheduling it again for April. So hopefully you will see that we repeated this experiment successfully in the near future. And of course, now that we've met this goal, we're looking toward our next big goal, which is producing tens of megajoules of yield on the NIF. Next slide. So what did it take to get to where we are now? A lot. It took exquisite experimental facilities, targets that are just engineering marvels, state-of-the-art high-performance computing and simulation capabilities, as well as physics intuition and understanding that was developed over the course of many decades of research, and an amazing team of researchers who never gave up on pursuing this goal. Next slide. So that kind of summarizes the overview of what the program looked like, what changes we've made to our designs over the years that led to the December experiment. So now I'm going to switch gears and talk about the part near and dear to my heart, which is how we called the shot before it happened. So next slide. So I work with a team in the ICF program called the Cognitive Simulation Team. For the last probably 6 years or so, we've been working on basically applied uncertainty quantification for experiments. We've been developing tools and techniques to help us quantitatively evaluate design sensitivities, use statistical methods to calibrate our simulation models to data. And more recently, we've been figuring out how to propagate those model uncertainties to new scenarios to make predictions of experiments before they happen. Next slide. So I mentioned earlier in 2021, we reached what we called the threshold of ignition. Once we exceeded the Lawson criteria with this shot 210808, and then repeated that experiment several times and didn't get as high of a performance. Next slide. So following this experiment, we had these repeat experiments to assess the repeatability, and the team I work with has been using this set of repeat experiments to answer some really important questions that we've really not been able to answer before. One of those questions is, what is the level of variability we should expect to see in an experiment? As hard as it might be to believe, we've actually never repeated an experiment on NIF that many times before. So we never had a good measure of what these shot-to-shot variations look like for this facility. Every time you field an experiment, the laser behaves slightly differently. The target is of a slightly different quality. And this was the first time we were able to actually put error bars on what happens if you just do the same experiment multiple times. So we're also trying to understand what drives these observed variations. What are the changes to the initial conditions in the experiment that can explain why we see such large variations in our performance. So answering these two questions is really challenging. There are a lot of unknown and correlated sources of performance degradation in our experiments. And these systems are highly nonlinear. So very small perturbations to, say, the smoothness of the capsule surfaces can lead to huge changes in the outcomes of the experiment. And it's made more complicated by the fact that we don't have a ton of data. We've only done, about 100 experiments on the NIF in total. And the experiments are not completely diagnosed. Like we can't measure all of the things we would like to be able to measure that would help us kind of formulate the boundary conditions for our simulations of these experiments. Next slide. So the cognitive simulation team is kind of making use of what we learned from studying these variability experiments to make predictions about future designs. So I've broken it apart into kind of like a three-step process. First, we infer degradation mechanisms that are consistent with the data from the variability shots, so from those actual experiments. We do this with a technique called Bayesian inference. Maybe you've heard of it before. The next step is to build a global model that quantifies our shot-to-shot repeatability. So you have uncertainties in your input conditions for a single experiment because we can't measure things perfectly well. And there are lots of ways to get the same answer when you run a simulation code. You have individual shot uncertainties, and then you have the shot-to-shot variations. So we fold those two sources of uncertainty together to build our global model. And then we apply this global distribution of degradation mechanisms to our new designs, basically to answer the question of, okay, if this new design sees the same perturbations that the repeat series of experiments saw, this is what we think will happen in the experiment itself. So step one is to understand each individual experiment from this set of repeat experiments. So we do this with a technique called Bayesian inference. Really what we're trying to do is solve an inverse problem using a computer model. So we have computer simulations of these experiments. And what we want to do is answer the question of, okay, what are the input conditions of the simulation that enable me to get outputs from the simulation that match the data? So we want to answer, typically you put in your input conditions, you run a forward model, a forward simulation, you get outputs. We want to take our experimental outputs and run the problem in reverse and say, okay, what simulation inputs would have given me these experimental measurements? So doing that with the simulation code by itself is really expensive. You do this technique called Markov Monte Carlo, which means you would be basically running hundreds of thousands, probably closer to millions of these really expensive simulations sequentially. We don't have time to do that. So what we do is we run a big ensemble of simulations that span a parameter space we're interested in, and then we train a deep neural network to basically emulate the code. That way we can run our Bayesian inference using our neural network instead of our real physics code. And at the end of the day, we are calibrated model parameters with uncertainties. There are lots of ways to match the data we observe on the NIF. We want to learn all of the different ways so we can keep rigorously account of our sources of uncertainty. Next slide. So part two is to build this global variability model. So we have in this middle panel here, all these colorful distributions, which indicate the uncertain input parameters. We're looking at two different input parameters on this figure. So we have uncertainty for each individual shot, the red shot, the orange, the blue shot. When we fold all of these models, these shots together, we get a global variability model. You can think of this as like when you go to the NIF and carry out an experiment, you're basically taking a draw from this distribution of possible outcomes. In one experiment, we drew the blue outcome, which had its own set of model uncertainties associated with it. The next experiment, we drew the red outcome. So this purple distribution kind of describes all of the different ways your implosion might be perturbed when you go execute an experiment. If we sample from this purple input distribution and run the forward model, so go run a bunch of physics simulations, We get outputs like what we see in this far right panel. Here we're plotting our neutron yields, how many neutrons we produce in our fusion implosions versus a quantity called the downscatter ratio. This is basically a measure of how dense our shell is when it's burning. Again, we want that good confinement of our fusion fuel, so we want a dense shell around the burning fuel. So this gives us a measure of that density. And the colorful points here are the actual experimental measurements of these two quantities for a series of experiments. So our purple global model kind of captures and explains all of the data we observed in this series of experiments pretty well. Next slide. So what we have in hand now is basically a distribution of simulation input parameters that match the data. What we want to do is take that distribution of input parameters and sample from it and apply those same degradations to a new design. So what we've been showing here are 2D projections of this distribution. In reality, the distribution is anywhere between 4 and 9 dimensions. So we're having a sample from a very high dimensional distribution of input parameters. We've developed efficient ways to do that. And then we can go basically propagate those input parameters through a forward model for a new design. Next slide. Unfortunately, we need a new forward model for this new design. So for all of this Bayesian analysis I was just showing you, we had a neural network that we had trained on the 210808 design that was very specific to that design. Making that neural network cost tens of thousands of high-performance simulations. So it's a pretty expensive endeavor. We didn't have time to go make a new neural network from scratch on our new design that we wanted to make a prediction for. We only had about a week to make this happen. So we ended up taking advantage of this technique called transfer learning that basically let us take the knowledge we had learned from our neural network that was trained on the 210808 data and retrain just a small portion of that network to shift its predictions to be in line with a new design. So we ran just about 32 simulations of the new design that was going to be fielded in December, used transfer learning to make a new neural network that could basically predict the outcome of that design as well as the forward model itself. So I'm happy to answer more questions on this. I know we have to go over it kind of quickly, but at the end of the day, what we got was a new emulator that mimics a new design, the one that we fielded in December. Next slide. So we can take those input parameters that we have from our variability model, our small set of 2D simulations for the new design, that we propagated through a neural network to retrain it. And what we get when we propagate this distribution of input parameters through the new design is a distribution of predictions. And we do this very efficiently, taking advantage of a technique like transfer learning, let us basically speed up the process by about 1,000 times compared to how we would have done it in the past. Next slide. So now we're ready to put our predictions together. We have our input parameters, we have our forward model. Now we just need to propagate those inputs through the forward model and make predictions. So we can go ahead and go to the next slide. So this is the exact slide that I sent out to our program management a few days before the experiment happened. We said that we expected this December experiment, which was actually a repeat of a September experiment with small changes to correct the symmetry. So it's kind of wordy, but basically we expect the December experiment to get 2 to 3 times the yield of 210808. Again, that shot had 1.35 megajoules of yield. And we said there was about a 50% chance this particular design would reach breakeven or produce more than 2.05 megajoules of laser or of nuclear fusion. So sending this slide out, from my perspective, was a pretty scary thing to do. No one had ever achieved ignition before. We've been trying for decades, saying, oh, we're probably going to do it this weekend. Felt like a pretty bold prediction, but I thought the team had done a good job. We were very rigorous in accounting for uncertainties and the way we modeled this implosion. So we sent it, and we decided we would just put our bets on the table. And if you can see the little square on this, the little yellow square on this plot, that's actually where the data came in. So it came in pretty similar to our expectations for the neutron yield, which was really exciting to see. If you go to the next slide. So we're actually predicting more than just the yield and this downscatter ratio. We can predict basically anything that you're going to observe at the NIF, a large range of observables. So I'm plotting on these plots, 2D distributions of other input or other output parameters we made predictions for, like the temperature of the hotspot and how long it was going to burn. And our predictions were pretty consistent with what we measured across a wide range of diagnostics. Next slide. Okay, so that was a brief introduction into how we made that prediction. Now we'll talk about where we're hoping to go with this in the future. Next slide. So this ignition shot had a gain of 1.5, and we said it had a greater than 50% chance of achieving that gain. Next slide. So that's basically a coin flip. That's not enough to make fusion energy reliably. So we need more reliable gain, and we need to get it all the time if we want to make this an energy source. Next slide. So there are some key questions we want to answer now. Can we find a design that reliably achieves high fusion energy production? And can we qualify that design before we field it? So can we do an analysis like the one I just showed you and say, there's a 95% chance this thing is going to ignite if you go do the experiment? Next slide. So this is a really hard problem, and you might get some respect for the problem if you try to think like a designer. If you look at your horum and your capsule and your laser that you can tailor to deliver your power however you want as a function of time, and ask yourself, like, what parameters can we vary to try to improve the performance of this particular design? And next slide. And the answer is a lot. This one doesn't even list the laser pulse as a thing you can vary in exquisite detail other than this one little parameter here. So you can change so many things about these experiments. You can change the shape of your horum. You don't have to use a cylinder. You can change the size of these laser entrance holes. You can change how you point the lasers into the horum. You can change what it's made out of. We use gold and depleted uranium for our horums, but you can use something else. With your capsule, you can change what the ablator is made out of. You can add all these different dopants to the ablator to give it different properties. You can add more DT ice or more fuel. There are tons of parameters that you have at your fingertips as a designer, and it's really a prohibitively huge design space. And we've only done 100 experiments at NIF, so we've only explored a very, very tiny fraction of the possible combinations of target and laser pulse. Next slide. So in order to push our performance even further, we're working to enable mission relevant optimization for these types of experiments. It's a really challenging problem. The design space is huge, like we just said, and we use computer simulations to come up with these designs. And these computer simulations are really expensive. To run one of these 2D horum simulations, they take like 3 to 4 days, on 32 nodes of one of the best supercomputers in the world. So they're really expensive simulations, and we're often limited to running 2D versions of a 3D system at low to medium resolution settings in order to do a lot of our design work. But we really want to be running at really high resolution so we can resolve very tiny defects in our capsule. And even better, we would like to be 3D simulations because our facility is 3D. And we want to do this and search through a huge parameter space for the best designs. And next slide. So we're hoping that exascale computing can help. We are currently working on a big project to automate ICF design for future use in the program. We're hoping that having an exascale sized machine like the supercomputer Livermore is getting next year called El Capitan can enable us to explore these really large design spaces and do new kinds of optimization, like find designs that are robust to these different types of perturbations that our experiments see. We're developing really efficient searching algorithms that take advantage of multi-fidelity simulations. So we run cheap simulations to explore a space and then expensive simulations where things look most promising. And we're developing highly scalable workflow technologies to let us do this on the largest supercomputer that will exist within an SA complex. Next slide. So this is just kind of a list of all the things that we're doing in this project, gearing up to run on El Capitan. I won't go through the list, but if anything here is exciting to you or you're interested in, please contact me. If you're looking for a job in the near future and this seems really cool to you, definitely get, because we're always looking for people to help us out. Next slide. And you're super excited about computers themselves. El Capitan has some really interesting hardware features about it that'll be really cool to test out. Next slide. Okay, so now we're getting toward the end of the hour, and I want to make sure people can ask questions. So I'll summarize really quickly that on December 5th, 2022, we had an experiment at the National Mission Facility, achieved fusion ignition for the first time in history. That experiment had a gain of about 1.5 and built on decades of multidisciplinary research and development. Next slide. So prior to this experiment, we used a combination of statistical analysis and machine learning to quantitatively predict the outcome. This cognitive simulation model blends our HPC simulation capabilities with experimental data with machine learning as kind of the glue in between the two. And we predicted that ignition was the most likely outcome for this shot. Next slide. So for the future, we're working on pushing ourselves to higher yields and more reliable high yield experiments. We're working to embed machine learning and these uncertainty quantification analyses into the design process so we can design for experiments that have a high likelihood of getting high yields. And we're going to be testing this out on El Capitan and NSA's first exascale computer in the next couple of years. I think the next slide, is my last one. Yeah, so thanks for your attention. Thanks again for your patience up top, getting technological issues worked out. I'm happy to take questions now and happy to have conversations. You can reach out to me via email as well.
All right. Any questions?
I'd have a question.
Yeah.
So you said that of course this is not something that's going to do a fusion energy in a sustainable way because you destroy it's a short burst of fusion energy and everything is sort of destroyed. But you said that people are working on trying to capitalize on this. Is there what kind of ideas do people have on how this might be used to sustainably extract energy?
Yeah, good question. There are a lot of interesting approaches out there. A lot of them involve first making this a high rep rate capability, right? We do one experiment and then we're done, and then the laser cools off for a few days before we think about doing it again, which isn't going to be sustainable for fusion production. So people are looking at these, petawatt laser systems, really high rep rate lasers, and different ways to feed in a capsule at a high rep rate too, right? So some people are doing the approach where it's just like gravity, you drop the capsule from the top of the fuel chamber and you have the lasers perfectly aligned to zap it at the right time. Other people have different ways of, moving the laser, and you have a series of capsules that you're trying to shoot in subsequent firings of the laser. All kinds of creative approaches, but they all have definitely engineering challenges associated with them.
So it might be another 30 years to see something coming from it.
Yeah, I think the timeline is really dependent on the investment, like the money and the people hours, right? Because we kind of answered the fundamental physics question of can you do it, and it's a whole different challenge to come up with a facility that lets you do it reliably around the clock. So it'll be a lot of investment from private and public spaces.
Any other questions? Bob?
So you've got these relative. What?
I'm just turning it towards you.
Oh. You've got these relatively complicated models which have an enormous number of input parameters that describe your system. And you have relatively limited observables that are coming out of the system, and you're doing the reverse model to predict what those input parameters are that describe the output energy. There's got to be numerous degeneracies with those input parameters. How do you deal with all those degeneracies? And how do you use that to guide sort of the next group of experiments that you do to try to increase the yield?
Yeah. I think I caught that whole question. One, what do you do with your degeneracies, this inverse problem? How might that help you decide what to do next with your experiments? If I'm hearing right. So yeah, it's these inverse problems are highly degenerate. And what that looks like at the end of the day for us is it looks like our predictions are pretty uncertain. And a lot of that comes from the fact that we're very uncertain of our input conditions right now with these experiments. So we're always looking for ways to reduce the degeneracies where we can. So some of that looks like taking advantage of more of the data we get at the NIF. So right now, our Bayesian analysis is focused on really scalar metrics, things like yield, temperature, downscatter ratio, just scalar observables from the facility. But we also take images, like we have multiple images of the implosion. They are they're spectral data that we get from these implosions. And what's really challenging is figuring out how to do a Bayesian inverse problem with an image or with spectral data. That's, in the statistics, that's a really hard problem. People haven't quite figured out how to solve reliably. So, in the background of our day jobs, we're also trying to figure out how can I use the image information to help constrain my models more of that degeneracy, but it's much a research area right now. And yeah, the second part of your question is like, are there experiments that we could do to help reduce uncertainties as well? What's interesting is there are, and we've actually done a couple experiments in the last year that are not like deuterium and tritium experiments. So they're not the really expensive, high laser energy experiments. They're smaller ones. They're ones without any fuel in the capsule that just tells us about some of the hydrodynamic behaviors. And it gives us data to constrain our models, even if it doesn't constrain like our neutron yield. We can still use these cheaper experiments to learn more about how to make our models better match different phases, different parts of the physics that's happening. We're always thinking about ways to improve our modeling and make it more accurate through these less expensive experiments as well.
We have another question way over there. Can't really, I don't know if I'm gonna be able to get you or not.
I was just wondering, because I know you mentioned earlier in your presentation that a part of the advancements of these experiments was actually utilizing larger capsules for more surface area to get like a bigger payout for the energy that you're putting in. And I'm genuinely just curious, like, have y'all tried different like shapes like helixes or folding or anything like that to increase the surface area, or does that like increase too much? Like, would that be too like invariable to do? Like, I'm just wondering.
Yeah, it's an interesting question. We haven't done anything as complicated as like a helix or a geometry like that. What we're really interested in is figuring out how to get our hotspot to high of a density and pressure as we possibly can. And it also needs to be like large enough and confined long enough to hold together so the fusion reactions have time to occur at a high volume. So we've been really focused on spherical implosions at the NIF. But that is a limit, like we have limited ourselves by only looking at spheres. The magnetic liner inertial fusion approach does something a little bit different, maybe similar to what you're thinking, and that it actually does a long skinny cylinder of fuel and uses magnetic fields along with lasers to squeeze that fuel to really high densities, and it's like a high density wire rather than a sphere. But those are the only two like big geometries I've seen people working with. But that's a super interesting design problem. Say like, okay, what if I want a non-spherical capsule? What could I do with it?
Any other questions? I guess I just have kind of a naive question that I'm sure that people have asked in some of these press conferences and things is, this is safe, right?
Yeah, yeah, we have gotten a few questions like that. Yeah, I mean, if you can actually be in the building at NIF when these experiments happen, and they're really not exciting at all because these explosions, while they're producing a lot of energy, they're not producing that much energy, and it's over a short amount of time. Like, it's a lot compared to what we've been used to seeing. But these implosions are over super quickly. There is quite a lot of containment of the facility. Right now, the facility itself is safely able to handle a neutron flux of up to 40 megajoules of neutron yield. So that neutron flux is really what you're worried about as a human being standing in proximity, right? They're very short-lived, but it's a lot of neutrons at once. So there is a ton of shielding around the target chamber itself to prevent any damage from the neutrons happening to electronics or any people in proximity. But yeah, it's a really the December experiment itself was since we were expecting that level of yield, they had extra protocols in place to make sure to get off safely. What was actually more interesting was the August experiment. We were not expecting to get over yield on that experiment. So they didn't put in the extra shielding. all the people were safe, but it actually did damage all of the fluorescent lights in the facility. So the, the lights went out in the rooms surrounding the target chamber right after the experiment. They had to replace all the light bulbs, but fortunately that happened.
That's interesting. Any final questions?
I've got another question.
Yeah.
Well, my questions just left my head. Oh, yes. So you mentioned at the beginning of your talk, there was a lot of applications that are sort of possible with this inertial confinement technique. For example, you could do things that are pre-fusion, like study the I guess we call it warm dense matter, like at the center of Jupiter. Have people been using the data? Is the data you've been taking up to fusion sort of applicable to studies of that sort? And are people doing things along that line?
Yeah, people are. These are experts kind of outside of my range of expertise. But NIF doesn't just do these ICF implosions. They do a number of other implosions that are dedicated to like astrophysics applications and certain measurements. From like what kind of radiation is materials at these particular densities and temperatures. So there are a number of things going on at NIF to improve measurements and understanding those conditions. And now that we are getting to a point where we can really produce these high yield conditions, I'm sure that people will be posing all kinds of things of like, oh, can I put this ride along experiment next to it so I can see what happens when this material is exposed to that flux or these sort of things.
Hey, thanks.
Thank you.
All right. Well, I think our time is up, so let's thank our speaker again.
And thank you, everyone.